Hello friends, once again I welcome all of you. Today we will see the air standard dual cycle. Now previously we learned the diesel cycle and Otto cycle. So though in those cycle, in Otto cycle the heat addition takes place at constant volume, whereas in the diesel cycle heat addition takes place at constant pressure. So in the actual cycle this doesn't happen. There is no chance that the heat addition will take place either at constant volume and either at constant pressure. So in order to approximate these cycles performance actually, so there is a one more cycle which is the combination of Otto cycle and diesel cycle. It is called as a dual cycle. So in this cycle the heat addition takes place partially at constant pressure and partially at constant volume. So we will see. So this is the PV and TS diagram for dual cycle. Here also we assume the working medium is air and it obeys all the standard laws, all the gaseous standard laws, and heat addition and heat rejection is done by hot spot and cold spot respectively. So here in this PV diagram, from process 1 to 2 there is a compression stroke. Now here the heat addition takes place partially at constant volume. From process 2 to 3 it is a constant volume process. Here heat addition takes place, and from process 3 to 4 it is a constant pressure process, constant pressure heat addition process. So from process 4 to 5 there is an expansion, and 5 to 1 is a heat rejection. So I will note here heat addition, and here heat rejection. Now the compression ratio is denoted by small r, which is nothing but V1 upon V2. From state 1 we compress this air to state 2, hence V1 upon V2 is a compression ratio, and expansion ratio is from process 5 to 1. Now the expansion ratio is here expansion ratio is denoted by alpha, which is nothing but P3 upon P2. Now the cutoff ratio which is denoted by small rc, which is nothing but V4 divided by V3. It is called as a cutoff ratio. Now we will calculate the thermal efficiency of dual cycle. Now the standard thermal efficiency formula, which is nothing but heat supplied minus heat rejected divided by heat supplied. Now here in this cycle heat addition takes place partially at constant pressure and partially at constant volume. So Q is equal to mCV delta T for heat supplied, so equation becomes mCV T5 minus T1 mCV T3 minus T2 and mCP T4 minus T3. So this is the formula for thermal efficiency. Now simplifying the thermal efficiency equation, efficiency is equal to 1 minus T5 minus T1 bracket complete divided by T3 minus T2 plus gamma in bracket T4 minus T3. This is the equation for thermal efficiency of dual cycle. Now in this equation we need to put the values of T2, T3, T4 and T5. We will reiterate this equation into, now for process 1 to 2, for process 1 to 2, T2 is equal to T1 in bracket V1 upon V2 bracket raised to gamma minus 1. Now we know V1 upon V2 is called as compression ratio, which is denoted by small r. Now we will put this value T1 into small r bracket raised to gamma minus 1. So this is equation 2. This we will call as equation 1. Now for process 2 to 3, for process 2 to 3, T3 upon T2 is equal to P3 upon P2 is equal to alpha. Now alpha is called as an expansion ratio. Now T3 is equal to T2 into alpha. Now put this value of T2 or equation 2 value into this. The equation becomes T3 is equal to T1 into r raised to gamma minus 1 into alpha. Now for process 3 to 4, for process 3 to 4, T4 divided by T3 is equal to V4 divided by V3 is equal to RC. It is called as a cutoff ratio. Now for equation T4, this T3 term goes to the right side, T3 into RC. Now we found out that value of T3. We'll put this equation value into this equation. Now this equation becomes T4 is equal to T1 into r raised to gamma minus 1 into alpha into RC. This is called as equation. We denote it as equation 4. Now last process. For process 4 to 5 is equal to T4 in bracket V4 divided by V5 bracket complete. Now we will put the value of V4 upon V5. T4 big bracket V4 divided by V2 divided by V5 upon V2 bracket raised to gamma minus 1. Now simplifying it, T4 into V4 divided by V2 upon V1 divided by V2 bracket raised to gamma minus 1. Now again we will simplify it for T5. T5 is equal to T4 in bracket RC divided by small r bracket raised to gamma minus 1. We know V4 divided by V2 is nothing but the cutoff ratio, which is denoted by RC, and V1 upon V2 is a compression ratio, which is denoted by small r. Now the equation for T5 becomes, putting the value of T4 into this equation, T1 into R into alpha into RC multiplied by RC divided by R bracket raised to gamma minus 1. Now cancelling out this R with R, simplifying the terms, equation becomes T5 into T1 into RC raised to gamma into alpha. Now we have found out all the values of equation for equation 2, for equation 3, equation 4, and this equation 5. Now put these all values into thermal efficiency equation. Now the thermal efficiency of dual cycle is equal to 1 minus bigger bracket alpha into RC bracket raised to gamma minus 1 divided by R raised to gamma minus 1 bigger bracket alpha minus 1 plus R into alpha into RC minus 1 bracket complete, big bracket complete. So this is the final thermal efficiency equation for dual cycle. Now we know for the same compression ratio, the thermal efficiency of Otto cycle is more than that of the diesel cycle, but we know that the compression ratio for diesel engine has a range which is more than the petrol engine. So there is a difference between the compression ratio of petrol engine and diesel engine. Now by approximating the performance via dual combustion cycle, if we put the value of alpha is equal to 1, then the thermal efficiency of dual cycle is increases. Thermal efficiency of dual cycle is increases. So from this equation we understand the thermal efficiency of Otto cycle is more than the dual cycle and lower is the thermal efficiency of diesel cycle. Thank you.